Hello, welcome to the course SJPHY2 B02 Mechanics 2. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. We will continue to discuss topics from Module 3, Harmonic Oscillator. In the last couple of classes, we were discussing about a simple harmonic oscillator and damped harmonic oscillator. And we have seen that in the case of a simple harmonic oscillator, the motion is completely determined by the restoring force. Now let's see what happens. In addition to restoring force, there is also another external force acting on the system. Now such a harmonic oscillating system is known as force harmonic oscillator or driven harmonic oscillator. So let's start with the effect of an applied time varying force f of t on a frictionless harmonic oscillator. Now such a system is known as undamped force oscillator. So let's assume a mass spring system as shown in the figure. An external driving force can be applied by simply jiggling at one end of the spring. Now when you apply this external force, the end of the spring is going to move with a displacement y equal to y0 cos omega t. Okay, so this is a sinusoidal variation in the displacement. Now let x be the displacement of the mass from its equilibrium position due to the restoring force. So now you have two displacements, one due to the restoring force. By convention, we know that the right hand direction is always taken as positive. So you have plus x due to the restoring force, and you have minus y due to the external force. Okay. So the total change in length of the spring from its equilibrium position is going to be plus x minus y. Now, neglecting the effect of damping, you can write the equation of motion as mx double dot equal to minus k into x minus y. Substitute for y, so minus k into x minus y naught cos omega t. Now, k into y naught, you call it as f naught. So your equation of motion now becomes mx double dot equal to minus kx plus f naught cos omega t. But this extra factor f naught cos omega t is the driving force. So even though we have derived this equation for the specific case of a mass spring system with the external force in the form of jiggling at one end, the form of the equation is quite general, because any periodic driving force can be represented by a combination of such sinusoidal force terms. So this is a famous theorem in mathematics known as Fourier Theorem, which basically says that any periodic finite function can be represented as a series summation of sinusoidal functions. So for any general scenario, you can write the equation of motion in this fashion. Now if you rearrange the terms, you can write mx double dot plus kx equal to f naught cos omega t. So this is the equation of motion of an undamped force oscillator. If you recollect the equation of motion of a simple harmonic oscillator, there instead of f naught cos omega t, the right hand side was 0, mx dot plus kx equal to 0. Now you know how to solve this equation of motion, right? You need to first write the auxiliary equation, find the roots of that, and from the nature of the root you can write the general solution. But we are not going to get into such a detailed derivation now. For now, we'll be happy with a qualitative analysis of the solution. So if you look at the right hand side of the equation, it varies in time as cos omega t. So it's possible that the left hand side also going to vary in the same fashion. So in other words, we are going to look at a solution x which varies as a function of cos omega t. So let's assume that Our solution is x equal to a cos omega t, where a is some constant whose value we need to find out. Now substitute this back into the equation now. So m into x double dot is minus a omega square cos omega t plus k into, instead of x I write a cos omega t equal to f naught cos omega t. Now a cos omega t is common, I take it outside, so I have minus m omega square plus k into a cos omega t equal to f naught cos omega t. Cancel cos omega t on either side. Now I can write a equal to f naught divided by k minus m omega square. From the denominator I am going to take m as a common factor outside, so the equation now becomes a equal to f naught by m 1 divided by k by m minus omega naught square omega square. From the previous derivation of simple harmonic oscillator, we know that k by m is nothing but omega naught square, where omega naught is the natural frequency of the simple harmonic oscillation. So I write the constant in the solution a equal to f naught by m 1 divided by omega naught square minus omega square. So my solution to the equation of motion x of t equal to f naught by m 1 divided by omega naught square minus omega square cos omega. Now this solution is quite different in nature from the solution of a simple harmonic oscillator or a damped harmonic oscillator. If you recollect, in those solutions you had some unknown constant like a, b, c, etc. And using appropriate initial condition you had to find out their values, right? But here you do not have any arbitrary constant, which means the motion is fully determined. But the catch is that even though this solution is correct, it is not complete. So the complete solution is given by x equal to this factor f naught by m 1 by omega naught square minus omega square cos omega t plus b cos omega naught t plus phi. I'm sure you are familiar with the second term. This is the solution of a simple harmonic oscillator. In other words, this is the solution of the equation of motion mx double dot plus kx equal to 0. So this term is known as the general solution, whereas the first term is the specific solution to the equation mx double dot plus kx equal to f naught cos omega t. Now in the case of a simple harmonic oscillator, this coefficient was a constant, but we know that for a damped system this amplitude is not a constant. This decreases exponentially in time, right? So after some considerable time this term essentially becomes 0, so we are left with only the first term, which is known as the steady state solution. Okay. Now let's discuss about one of the important aspects of a forced oscillation or a driven oscillation. So this is known as a resonance. Now if you look at the coefficient in the solution, or the amplitude in the solution, amplitude A is given by f naught by m 1 divided by omega naught square minus omega square. So let's plot amplitude A as a function of the driving frequency omega. So this is the graph. So let's start with the extreme point. As omega tends to infinity, the denominator becomes infinity here, so the entire term becomes 0, right? So you start with 0 here, or almost equal to 0 here. Then look at the other point. When omega equal to 0, then A is f naught by m omega naught square, which means it has some finite value. So this is the starting point. Okay. Now let's look at the middle point at omega equal to omega naught. What happens? So omega naught is the natural frequency of the simple harmonic oscillator. So you are going to drive the oscillator at its natural frequency. So when omega equal to omega naught, the denominator becomes 0. So the entire factor approaches infinity, right? So A increases without limit when the oscillator is driven at its natural frequency. This great increase of amplitude when a system is driven at a certain frequency is known as resonance. So in this particular case, resonance happens at the natural frequency. So natural frequency omega naught is also called as resonance frequency of the system. Now this equation predicts that at resonance, or when omega tends to omega naught, A tends to infinity. But we know that in any practical system, it is impossible for the system to have infinite amplitude. You can have extremely high amplitude, but infinite amplitude, that is not a real possibility, right? So this conflict is due to the fact that throughout our analysis, we have neglected the influence of friction. So if you take the effect of friction into our analysis, we will find that at resonance, the amplitude is going to be very, very high, but not quite infinite. So it is going to remain finite. So this is what going to happen in any practical system. At resonance, the amplitude is going to be very, very large. It's clear from the graph that when omega is less than omega naught, when driving frequency is less than the resonant frequency, so we are talking about this particular portion, here the amplitude A is positive. On the other hand, when omega greater than omega naught, this portion where driving frequency is greater than resonant frequency, amplitude A is negative. Negative amplitude means that if the force varies as cos omega t, then the displacement varies as minus cos omega t. Since minus cos omega t is cos omega t plus pi, basically this negative sign indicates that there is a phase shift of pi radians or 180 degree between the driving force and the displacement. On the other hand, when omega is less than omega naught, the amplitude is positive, which means displacement is in phase with the driving source. So whenever the driving frequency is less than the resonant frequency, the displacement and the driving force are in phase, as when the driving frequency is greater than the resonant frequency, then the displacement is out of phase with driving force by a factor of pi radians. I can demonstrate this with an example. So you break a long rubber band and suspend something like a heavy pocket knife from one end, holding the other end in your hand. So this is like a simple harmonic oscillating system, right? So you basically pull the mass slightly downwards and release it. It's going to execute simple harmonic oscillation with its natural frequency omega naught. So in this particular context, we can call omega naught as the resonant frequency. Okay. So the free motion is going to take place with resonant frequency omega naught. Okay. Now if you slowly jiggle your hand at a frequency omega minus omega naught, now the simple harmonic oscillating system becomes a force harmonic oscillating system, and the driving force omega is less than omega naught. So we know that in this particular case, the displacement is in phase with the driving force. So the weight will move in the same direction as your hand, as indicated by this purple diagram. So arrow mark indicates the direction of the driving force. You can see that the driving force and the displacement are along the same direction. Now if you jiggle the system with omega greater than omega naught, driving frequency greater than the reference frequency, then what happens? The displacement is now pi radians out of phase with the driving force. So you will find that the weight moves in the opposite direction to your hand, as indicated by this red diagram. See, when the force is in upward direction, the displacement is in downward direction. Now if you try to jiggle the system at resonance, omega equal to omega naught, the amplitude increases so much that the weight either flips up in the air or hits your hand, as indicated by this blue diagram. See, compared to these two conditions, amplitude of oscillation is very, very high when you drive it at the resonant frequency. Now, the phenomenon of resonance has both positive and negative aspects in practice. By operating at the resonance frequency of a system, we can obtain a response of large amplitude for a very small driving force. This is particularly utilized in many electric circuits. For example, if you want to tune stations in your radio, what it make use inside is a resonance circuit known as LCR circuit. So here L stands for inductor, C for capacitor, R for your regular resistor. Okay. So basically this circuit at its response is frequency dependent. At resonant frequency it gives maximum output. So we know that in our air all sorts of radio frequencies are available. So if you want to tune to a particular frequency, so what happens, you tune your LCR circuit. Now if the frequency of your signal matches with the resonance frequency of the LCR circuit, then the LCR circuit captures this particular signal, and we know that at resonance the output is going to be maximum. So the output of the LCR circuit is then given to an amplifier circuit, and basically the signal will be amplified and played through your radio. Now if you want to change the radio station, what do? You basically turn the knob on your radio, right? So when you turn the knob, what happens is the knob is connected to a variable capacitor. So basically capacitance of the LCR circuit changes. So when the capacitance changes, by default the resonance frequency of the LCR circuit changes. So now what happens? The resonant frequency will match with some other frequency in the spectrum. So that frequency will be captured by the LCR circuit, and by virtue of resonance that frequency gives maximum output. The output will be amplified by the amplifier unit and will be played through your radio. So this is how you make use of the phenomena called resonance to tune radio station. So this is one of the important applications of resonance. There are several other important applications. But resonance also has a flip side to it, a negative side to it. Especially in automobiles, we do not want motions of large amplitude in the springs of an automobile or in the crankshaft of its engine. Why? Because if you have large oscillation, it's basically going to throw the automobile out of its equilibrium response, right? Resonance is also very bad when it comes to long bridges, especially suspension bridges. Okay. So if you look at a very long suspension bridge, it has some inherent oscillation. So it has a natural frequency to it. Now if you apply a very high external force, and by chance if the driving force matches with the natural frequency of the bridge, then the bridge is going to oscillate with very high amplitude. So that can cause damages to the bridge. So this is exactly what happened in the case of Tacoma Narrow Bridge collapse in the United States. So this is often described as a classical example of force harmonic oscillation. So Tacoma Narrow Bridge was a suspension bridge built in US in the year 1940. That time it was the second longest bridge in the world. So as I said, a suspension bridge has its own inherent oscillation. So this bridge was commissioned in the month of July, but within 4 months, in the month of November, it was collapsed on its own. So what happened was, during that particular day, November 7, there was heavy wind in that area, and wind can act as an external driving force, right? And it so happened that the frequency of the wind and the natural frequency of this bridge matched. So the bridge went into resonance condition. So it started oscillating with very high amplitude as shown in this schematic, and eventually it got destroyed on its own. So this is a classic example of the negative effect of resonance in a forced harmonic oscillating system. So many a time people want to avoid resonance in oscillating systems. So what they do to reduce the response at resonance, a dissipative friction force is induced into the oscillating system. Now such a system with a dissipative frictional force is known as forced damped oscillator. Incidentally, most of the practical forced harmonic oscillator systems are inherently damped in nature. So even though I explained the Takamoto bridge collapse in terms of resonance, in reality it is not that simple, because a detailed investigation revealed that the collapse happened because of something called aeroelastic flutter, and the aerodynamics behind it is pretty complicated. But as a first degree analysis, we can say that the collapse happened because of resonance in a forced harmonic oscillating system. So that's for today. With this, we come to the end of module 3. Thank you for being with me. Bye.